Let's move now to capabilities. In this case, we associate a list of permissions to each domain process. Each entry in the list is a capability, a file, or another object, and the set of rights associated with it. Since two domains can have part of their capabilities lists overlapping, they could use pointers to point to other lists hierarchically. Also in this case, we can have the common read, write, and execute rights, as well as other additional rights that are specific to a certain system or operating system. We can ask ourselves how to prevent a user from altering his or her capabilities. One way is to use a so-called tagged architecture. In this case, each word in memory, the word is the unit of data used by the processor, has a special bit, the tag, that if set indicates the word contains a capability and can only be changed when in kernel mode. So by an operating system process or a trust process. A second way to go is to keep the capabilities lists in OS memory, so user processes can point to them but not alter them. Finally, a third way to go, which is particularly useful in distributed systems, is for user processes to prove their rights are indeed correct when using files maintained by remote servers. This technique simplifies the sharing of files and rights in distributed systems. Let's assume we have a cryptographically secure one-way function f. It means from x we can compute y as f of x, but from y it is infeasible to find out x. In this case, when a file is created at the server generates a random number called check and returns to the client the file ID, the rights, and f of file ID, rights, and check, without giving the value of check back to the client, but rather storing it locally. When the client wants to access the file, it shares the ID, the rights, and the value of f. The server recomputes f, taking the file ID and rights from the client, but the check from its tables. If the values match, then the rights claimed by the client are correct and the request can be honored.